If you're looking for building a better understanding of kotlinx.coroutines, try re-implementing it. Coroutines in the Kotlin ecosystem is almost synonymous with kotlinx.coroutines. And it's quite fascinating that kotlinx.coroutines is just a library maintained by the Kotlin libraries team, and that you have all the necessary tools for re-implementing it in the standard library and within the Kotlin compiler. Let's try. Here we have a very plain and simple Kotlin main function which we can run. There are no surprises, it will greet us with a hello. However, there is also this async function which could print async. Now, calling this function with kotlinx.coroutines would be as simple as launching a new coroutine in some scope and invoking async. In this video, I'll show how to implement the basics of kotlinx.coroutines, such as invoking this async method, dispatchers, and switching context by providing our own with_context method. We can create the first coroutine taking any reference to a suspend function and create a coroutine from it using the create_coroutine function. Now, this create_coroutine is coming straight from the Kotlin standard library. This function requires us to provide a continuation. This object will care about two things. It will carry the coroutine context of the coroutine. We'll pass an empty coroutine context for now. Second, it provides the resume with function, which gets invoked once the coroutine finished. In this case, we're getting the value, or we want to throw on any error. Finally, the last remaining thing to do is execute this coroutine. We use this resume function, pass in unit, and this should actually then start launching this coroutine. We can see, yes indeed, there's an async printed out to the console. We called our first suspend function, and we see it being executed. Let's define a dispatcher interface as an abstraction over actual threads that can execute code. The interface can be very simple. We just want to dispatch any arbitrary piece of code to some kind of thread or queue or whatever. Implementing coroutine context.element will allow for providing a given dispatcher implementation in the current coroutine context. It's a quite common convention to use the companion object as a key for the coroutine context element. Now that we have defined the dispatcher interface, it is time to re-implement the main dispatcher. This main dispatcher allows scheduling tasks on the main thread. Typically, such a main thread is implemented by looping over a blocking queue. We're using a linked blocking queue here, which will block the current thread if there's nothing in this current queue and it wants to take some element from it. But every other thread could just use the .offer or some .add methods to push some runnable tasks to this queue. For this video, I'm using the poll method with a timeout, so that if there are no new tasks scheduled on the main thread, the loop function will just return. Now that we have a working main dispatcher implementation, we can pass this main dispatcher as the coroutine context to our continuation and use the main dispatcher to resume this first coroutine. Afterwards, we'll loop and instruct the main thread to execute all tasks on the main dispatcher. Right now, we have not really gained a lot. Yes, we have created a main loop for our main thread, but where's the fun without dispatching some kind of work to some kind of background threads? We can implement a background dispatcher which is backed by a thread pool. For the sake of this video, let's keep it simple and just use a thread pool with a fixed amount of background threads. Of course, in the real world, one is required to carefully think about the requirements of such pools and make sure to properly close them if not needed anymore. But this is YouTube. Yay, this was simple. We have now a main dispatcher and a background dispatcher implementation. Let's implement a with_context method to switch the coroutine context, which is effectively allowing us to switch threads. Note, this implementation would look different if our dispatchers would actually implement continuation interceptor. Let me know if you're interested in learning more about this case. This with_context method itself should be a suspend function that accepts additions to the coroutine context and another suspend function which shall be executed in the new context. Using the suspend coroutine method allows us to suspend the current running coroutine and provides us the outer continuation as a handle to resume it later. Once the current coroutine is suspended, we can create a new context and a new coroutine again using the create_coroutine function. Creating the new coroutine requires creating a new continuation, which of course gets past the new context. However, the resume with handle is important as it requires us to connect the new coroutine with the currently suspended one by resuming it in its desired dispatcher. Once the new coroutine was created, we can execute it by resuming it on the dispatcher found in the new context. Let's now bring it all together by going back to our main function and async function. We want to print the count thread's name that executes this async function. We can try out our with context function to switch to the background dispatcher. We also want to check if we are executing in the correct thread, so we print out what thread we are. Let's try out just switching back to the main dispatcher, again printing the count thread. And maybe it's interesting for us to check also if returning to the original async function is now also done in the main thread. Let's execute the code and see if we're actually in the correct threads. And yes, indeed, we see async is called at main, that we changed to some background thread, we changed back to the main thread, and the async function finished in the main thread. This is it, folks. Let me know if you want to see more about coroutines, and as always, have fun with Kotlin.